Many real-world problems involve springs, which are devices whose force changes depending on how far they're stretched. This includes the springs that you're used to considering, like metal coils and things like that, but also things like rubber bands and bungee cords. We're going to restrict our attention to springs that can be modeled as linear springs. Linear springs, which represent most of the real springs out there as long as they're used in their typical applications and not stretched, say, too far. Linear springs, the force is proportional to the stretch, and so we have a relationship for the force in the spring that looks like K times X. K here is called the spring coefficient, and X here is the amount that the spring has been stretched. So just to be clear, if we had a spring and if you didn't touch it, it would normally be, say, this long, and then you grabbed it and stretched it till it was this long. The stretched distance is here, x. We often call the unstretched length x0, and then we could say the overall length here is L, and that's equal to x0 plus x. So you want to be careful because the force part of this only involves x, not x0. So how do we model systems with springs in them? Systems with springs. How do we do it? Well, actually not too bad. We're going to take the spring out and replace it with a force on the free body diagram, and then just recognize that that force is always given by the relationship kx. And so really what we've done is we've just added one more equation that's going to end up in the mix as you solve for unknown forces and distances. So for example, we could have, say, a spring with a box hanging from it. And that box has a weight that pulls down on it. And so the free body diagram for this system is going to look like the weight pulling down and the force of the spring, which we usually do a subscript k to indicate that it's a spring force. Fk is equal to k times x. The only thing you need to be careful about with all of this is that we get the signs right. So I'm going to make a little note here. Be careful with signs, because if you stretch the spring, we'll call that a positive x. So for example, if this were the original length of the spring, so we could call this distance here x0. If I came and yanked on this thing until it came out to here with some force Fk, we could write that as kx like we've been doing, where this distance here is x. And if we wanted to, we could even define a coordinate system and put a little I hat on this and make it a vector force. Here's the thing. We can compress a spring. And so if we take that same spring with the same initial length x0, I'm going to write it above so that we don't get too much crowding here. But now I come in and I push on that spring with Fk in the other direction here. This distance now is our x, and it's a negative number because we've compressed. And so we would write this as kx, but if we wanted to write it in vector form, we would need a minus sign there. So just be careful with that, and we'll be okay. Either way, that's the trickiest part, and all we need to make sure we do is draw that free body diagram and assume a direction if you don't know, and the details will solve themselves. Essentially, you'll either get a positive or a negative number, and if it's negative, you just have to interpret what that means, and usually it means the spring was in compression instead of tension. So, how do we solve spring problems? The same 4 steps we've always done. We're going to start by drawing the free body diagram. We're going to write the force balances. So here we'd have the sum of forces in x and y, for example, or x, y, and z. The only new thing is that we also get to add an equation to the mix. We get to add the spring force model to the mix, which just says that Fk is equal to Kx. And so we get an extra equation in the mix that we get to use to simplify our efforts. Then we work out the geometry just like we've always done. So this will be things like sines and cosines to get forces resolved into angles. And then lastly, we'll have an algebra problem on our hands where we can solve for all kinds of things. Unknown forces, we could solve for the unknown stretch in the spring, whatever it is that we want to do. Point is, follow the same 4 steps and you will be able to construct a system without getting stuck.